Hi, my name is Hamid Ould-Brahim. I'm a product manager on the Nokia SDN platform, known as Network Services Platform, or NSP. I'll be talking today about how we addressed automation and optimization in the context of peering environment. So we're seeing more and more from a number of customers, whether enterprises, service providers, web scale, coming with requirements very frequently in their RFPs as well on how to do better, how to operate better the peering environment. Operate better in sense that they want the things that are coming more frequently, like performance, for example. And performance is not just from the border router to certain destination across the internet, but performance end-to-end. So that element actually coming from more on the web scale players and enterprises. But service providers are as well interested in how we can automate and simplify the operations on the peering for, let's say, inbound traffic, for congestion situations. Today, the way they are operating is like, they have like a number of it's typically they have team monitoring traffic utilization, and then when there are problems, they go start configuring BGP, and that process may take longer. In fact, they may not even just do BGP changes. They may do it even on the edge of the network versus to influence the border router, depending how their BGP model is being implemented. So we're seeing as well CDN, quality of experience being a concern. So for example, CDN resiliency. So let's say it's not necessarily, when the network is working in a steady state, but when things happen, maintenance happen, failure situations where a local POP fails and they have to get the content from a remote POP saturating the uplinks to the local POP. So wanted, can we do better to detect automatically congestion, understand the traffic, and maybe being smart what traffic needs to be moved to what resources that is available. So we looked at all this set of problems and this set of requirements. And we looked at what's today, the reality of today, which we know, some of it we already know about it. So first of all, the limitation within the protocol, the toolkit that we use. Today, BGP is the dominant protocol for the inter-domain routing within the internet part and service provider part and the customer part. But clearly, it's unaware of capacity, of real-time capacity. So the decision where to route the traffic is really based on criteria that existed like 20 years ago. Nothing has changed, really. We innovated from carrying services like VPN services, but we didn't innovate much on the decision process. So the shortest path may not be the best path considering the reality of the traffic of today, the application of today. The second thing is really performance, real-time performance. There are solutions today, even in the last 5 years. There are companies that specialize in trying to improve the route, manipulation, finding the best optimized low latency from a given border router to a given destination. But the solution is a bit more, they provide a partial solution to the real problem, which is an end-to-end latency, better latency for certain traffic that requires from the edge of the network to the destination. And as well, we've seen with the analytics discussion, the limited insight and visibility. What we know today, what we've been doing, you talk to how we operate. We know about the prefixes, the statistics, the ASs. These are the building blocks, but are building blocks tied to the protocol itself. So now we know a lot of things about the traffic. What can we do with it? That's a key question a lot of customers ask us. What can you do with all this traffic? What can you do is really, to answer it, is really you need to bring now the control, all the knowledge, how we build IP networks and tie the two together. So I'll be talking about concretely what the use cases we've been addressing, how we addressed them, And as well, giving you as well demo on that. Reda will do the demo on the actual use cases. So let me okay. So the approach, the framework is a closed loop automation, which means like you have a software, you have an SDN platform that receive insight from analytics, whatever that insight. In the context of deep field, we're taking full advantage of the cloud genome capabilities, feeding the controller, which is a software, and the software will have to act on the network by doing network changes. Not necessarily on one node. The use case may imply the changes on a number of nodes that realizes the use case. So what we've done, we developed what we're calling the express peering software delivered through the Nokia, the NSP platform. And this software, the way we approached it is really, when we looked at the peering, we came to conclusion there is not really one solution that fits all. And it's not only a protocol approach. It has to be viewed as three things, sorry. The insight, what the BGP operational model each, let's say, service provider or enterprise implement, and there are a number of them. It's not like some prefer communities, some prefer to act on prefixes on the border routers. Some, they do a model where they configure the policies on the border router, but the actual action and changes is happening at provider edge. It's like distributing, by analogy, cards. If the prefix has a set of cards, it means that prefix needs to go to transit provider A versus transit provider B. So that hidden design BGP to automate, to provide really a peering automation that really meets goals and objectives, we need to reflect that number of designs into the SDN platform, and then bring so that level of customization is built in, has to be built into the solution, and present in itself a challenge because there might be a number of designs, but what we came up to observe, it's only a small number of these BGP models that covers 80–90% of all deployment of today. So we will show you a bit more how this works. So in addition to that, so we took the approach of applications, different applications that control, let's say, inbound traffic, that controls outbound traffic based on latency. Typically, outbound is really, most of the requests are around latency, not about bandwidth, not even about cost as well on the peering side. So, and we did as well what's called the AS optimizer, where we're trying to optimize only based on destination AS for traffic coming from a DC to the external network. And the protocol side, we implemented a number of protocols within the app that we call Traffic Steering Optimizer. Southbound, now it's really the mechanism, the knobs, what will help us to really realize these use cases. So in this case, to realize these use cases, each app is actually a category of use case. Each app will have its own map, its own environment. So it's no longer like in the management world, you have an IGP map, and that's the only map you deal with. We came to conclusion to solve the automation optimization in the peering, we have to have a mechanism such that each use case has its own toolkit associated with it. Map, analytics, understanding the nature of traffic, that is maybe specific to that use case. So in terms of protocols, so you have a number of protocols, but typically what we need to realize on the, to implement on the peering automation, you need capability for traffic steering. So either flow steering, for example, so you need mechanism protocols that allow you that. You can achieve that through, let's say, BGP flow spec, OpenFlow, netconf. You can instantiate filters and manipulate live traffic on that. But they are even more a bit complex now coming into the industry, like BGP segment routing TE policy, which includes, if you want, a traffic engineering path, but the ability to steer BGP routes that have been tagged with certain color and match to the actual tunnel that you want to ship the traffic. That's done as built-in within the protocol. So these are like coming type technologies. And you need to be able to discover topologies. So BGP-LS will be a good protocol to do that. We needed as well the ability to have a bit more complex path computation. To compute a path from a source to a certain destination in terms of latency, we needed the construct to allow us to compute the path and algorithms based only on latency, for example. In addition to that, now you may have as well using ribbon fib API, which is another steering mechanism. So in this case, so let me elaborate about this building block and as well about the use cases. One advantage of being actually tied to a big analytics engine is we can do things we couldn't do before. For example, when we do traffic steering today on most of the routers and IP networks, we screen the IP packets, source destination, TCP, UDP port, 5-tuple, and we shift the traffic to, let's say, next hop, a tunnel, or even a VPN, for example. But if you have access to all this big data analytics, like the deep field we have, then I can do traffic steering based on macro data set. Move, for example, CDN traffic for that particular set of CDNs. It implies move the set of BGP routes associated with that traffic. So the SDN platform, the NSP, will then build a transactional traffic steering system, and then feed that, get that information from the deep field, build the actual actions, and steer the traffic with it. So it opens the door to a more flexible, more dynamic traffic steering that we couldn't do before. So let me describe a bit the use cases we have. So first of all, controlling inbound traffic. Controlling inbound traffic is becoming extremely important for a number of service providers. Why? Because they are receiving, they have a lot of peers, different transit providers, in different regions. They receive a lot of traffic from the internet. It saturates their link to certain thresholds, and they want to be able to shift traffic dynamically. And you will notice in the controlling inbound traffic is we're getting more and more requests for full automation versus operator, an operator manual mode, but with certain abstraction. We're seeing a lot of interest in and even requests where to do full automation. But full automation has to be in a controlled fashion. Cannot be, it's not like a buzzword we use, and concretely what we do on the solution and design has to really meet certain criteria how we operate the network. If you the way most of these service providers, they want to be able to detect congestion, automatically identify the traffic, and through an algorithm decide what traffic needs to be shifted where according to the bandwidth on the egress on the peering links. And in addition to that, they may as well want to say, I want to, traffic, I may have an international POPs, local POPs, and I want to be able to even optimize within that segment simultaneously in an automatic fashion. In the context of BGP, we actually find out the model that fits nicely with automation is manipulating communities. A number of these providers, they play with communities to act on the network. So so it's not the complexity of, let's say, you do the existing BGP nodes like AS, prepend, MED that you do on the border router, the policy, but actually how they choose the numbers of the community and they match them. They inject them here, they match them here, and if they get a match, it means move traffic from this link to that link. That model can be fully automated because it's just about distributing how you realize the algorithm will start just to find what's the best set of communities to distribute to shift the traffic. So we're going to show you actually a demo in that environment. So let me mention one of automation, if you want, consequence we came when we started implementing it. We realized it's not enough to use just a protocol set. We needed a construct that can be orthogonal to the reachability. So we needed a construct that will allow us to say, this router and this, I want to optimize within this router, this edge router, this region. So we developed what we call the optimization slice. So the operator will come, set them once, and discover as well, auto-discovery of the routers. So he's going to say, keep the optimization within this slice. If you don't find, for example, bandwidth within that router or that slice, then look elsewhere. So these things we cannot do it easily with the existing routing protocols. So you need to be able to dig down into the actual element of the protocol to realize it. And typically, once you do it, you don't want to touch it because it's a risky change, right? But in the context of when you do automation case, if you define the problem through an optimization slice, then your macro set will become move from slice 1 to slice 2, slice 3 to slice 4, and it turns into the algorithm will find out what the actual changes needs to happen into the network. So that concept has helped really how to realize the use case for inbound traffic. In addition to that, we're operating on a brownfield environment. So in this case, we need to keep the same functionality of BGP. So redundancy, we don't want to override existing behavior. We want to complement it. So if you look at, so things like redundancy needs to be taken into account in the algorithm. Things like ECMP. Most of these are already deployed. So we have to have the algorithm, the automation algorithm to take that into account. So in this case, if you are moving, for example, community, you will say, look, I will move it preferred to this one, but I will already plan the algorithm. What are the alternate if this one is not failed or hits certain thresholds. In addition to that, so now you can do things we couldn't do before, like tagging the links and that tag may have a business meaning versus a routing meaning. For example, it may be low-cost link, it may be low-latency links, and the algorithm will start moving traffic considering that filter, if you want. In addition to that, you will have hierarchical optimization. This is a lot of service providers found that very useful because when they design, they implement existing solutions in their network, they take that already into account. They know that, for example, these routers are in New York, and they know through their name exactly where the traffic will come. So this will help them to say, if you optimize within New York, keep within New York. If you don't find, start within, for example, closer to New York and so on. So the second category of use case we will show you as well is really the latency aspect. The latency is an important use case. We find it in the industry known as the egress peer engineering. But what we have, let's say in the IETF, we solve it just how you set up your path and how you pick the egress peer link. So the EPE job is really to engineer an egress peer link, an egress border router, an egress peer link from an edge network. This use case is very useful for CDN customers, for example. Why? Because if they need to be able, if they lose certain content sources, they want to go to their router and say, pick this one, not only this one, but pick the egress peer link, which we cannot do with BGP today. BGP, when traffic gets into the peering, it's a local decision of BGP to send the traffic to whatever. If you're multi-home, it's going to send it there. So segment routing actually adds some capabilities in that space because you can program the whole label, including the egress peer link segment ID, directly into the peer router. But the way we approached it is, in addition to segment routing, we wanted to solve it from a comprehensive point of view. Yeah, so I'm almost done. So what we're doing is really to measure from the border router to the external address what is the latency, measure it internally through the MPLS tunnel, add the two values, compute the total value, and inject that into the path computation algorithm that will figure out not only what's the best egress peer link, but what's the best router and the best egress peer link to reach really that user with lowest latency end-to-end. We will show you actually a demo on that aspect.
Hi, my name is Reda Laichi. I'm part of the IP consulting engineering team. As a follow-up to the previous presentation about peering either ingress or egress traffic, we selected very quick demos in both categories. Category number one is the inbound traffic, trying to solve problem of congestions or other type of KPIs, and steering traffic when possible, either automatically or operator triggered. And also, we have another demo that addresses actually the other side of traffic, egress traffic, for either performance or, again, other type of SLA, or in our case, we picked latency as criteria or constraint to be able to find an alternate path with the lowest latency possible. So let's start with when an operator jumps into the applications. As Hamid mentioned earlier, it's part of the NSP, Network Service Platform. There's a bunch of other applications there that could be either working together with the peering solution, or could be the peering solution could be a standalone applications. We have a bunch of traditional FCAPS application, as well as a PCE control that could be used in conjunction with the peering solution to do EPE, for instance. It could be part of the steering traffic. We could create LSPs or links to steer the traffic. Let's start quickly with the inbound traffic that are operator triggered. So when the operator log into the application, pick which type of use case solution, it gets presented with the network. So in this case, the network is two routers to simplify the demo. As well, you have a logical views on how you want to group your network. Two routers with two interfaces. Hamid mentioned the concept of logical slicing your network for business reasons, for the steering to stay within the slice or through the slice, for either geographical reasons or other business reasons. So that's why you see slice one and slice two. So this is my routers. Those are my neighbors, and you can see traffic is flowing. If I click on one of them, show me the traffic's flowing from the neighbors into my network as inbound traffic. So colors are indicative of the threshold that you have set to trigger to, in this case, is operator trigger. So give you an indication that something is about to be congested, and you can customize that threshold. So if I look in here, on the right side, it's very important. This information is coming actually from the D field that was presented earlier by Andrew. All this analytics that D field does on the interfaces as well as the bandwidth, it provides, for instance, top ASs here that are contributed to that congestions. So I know right away that interface, how much traffic has, and where's the traffic coming from that may cause me congestion in my inbound traffic. So I looked at it. I can decide to steer as an operator, or I can decide to look at other interface. So in here I have two type of top ASs that are causing traffic. So let's say try to steer. What it does, the application still give me all the information I need to be able to steer the traffic. So if I select, for instance, an AS here, it says, if you want to steer this AS, you have 3 alternate paths on the right side. It's a huge added value compared to blindly in the traditional way to do this kind of information like Hamid, or setup, as Hamid mentioned earlier, is to actually play with metrics and BGP and so on, which could be dangerous. In this case, it tells me you could move this to slice 1. And not only this, it's also providing me with the projection. If I move that kind of traffic to that alternate path, here is how much the alternate path will traffic in. Is it going to be congested? Is it going to be able to handle that traffic? So I pick one here, and then I can look at the details. What am I steering here? It gives me the information, and then I actually go finish, and basically what it does is start taking that AS that I have selected, and configure the policies to be able to steer the traffic to the alternate path that they selected. And you can see slowly, eventually slowly, the information will flow from that particular interface on the router into the alternate interfaces.
And you're basically automating things like all those variables within BGP to make this traffic decision? So
yes.
your prepend, your
Correct.
local preferences, things like that?
That's right. That's right. So in addition to that, it's really not just automating the set of actions, but where the action has to happen, where the deployment. In this particular model, you have the action happening. If you show Reda the topology, no here, yeah, this one, no here, yeah. If you show the peering topology, so that in itself represents category of BGP model. So you will have to the injection of these policies are done here,
right,
and communities. Matched here, which here, then they start, playing, set the med, if that number says AS prepend and so on. So it's a bit more than just injecting, the normal BGP policies, if you want.
Yeah, so it seems like there'd be an assumption that, that BGP is configured even correctly to begin with, and then given all the other analytics, you can start making more intelligent decisions on where this traffic's supposed to go.
Absolutely.
Correct, yes. You could be in a scenario where if I pick, for instance, as you have seen now, we shift a little bit some traffic. So AS, the 113 here was not in this link. Now it's shifting slowly to it. If I pick another interface and I want to steer it, for instance, it would be cases reality that I have no alternate path to this. So I have to live with that. So there's no alternate path to basically steer this or this particular IS. So we do also have a fully automatic solution to this where an operator does not trigger anything, and basically we call that autopilot, where the application does all the calculation and choose the alternate path based on policy and keep doing it down on a regular basis.
Yeah, you can. Let's try it. Yeah.
We'll jump into the latency one. So, so we looked at the inbound traffic. Either fully automated, where the operator just looks and look at the logs, what happened, why we steered, the number, what's the threshold, and so on. And don't forget that you have, as an operator, you have control of the threshold and how you want to steer traffic. We looked also at the operator triggers, with all the information fed to the operator, but the big red button still the operator had to push. But the application helps the operator by giving the simulation and what-if scenarios. Now we jump into trying to addressing the egress solution or egress peering challenges. So that could be congestions, same as before, or could be some other KPIs. In this example here, what I picked is really a criteria is latency. So what we have in my network get discovered automatically, part of the application monitoring, real-time network, and so on. So I have my PEs here on the left side, and I have my boarding routers, and I have the application that I'm interested in. I'm interested in a list of applications that could be my enterprise or business application, or could be something like a regular, Netflix and so on, or other type of commercial applications. So in the background, I am measuring and tracking latency from each PE here all the way to each application. And I can see that, for instance, in here, those are the current list of source PEs and the application, and in here you will see the latency that's being calculated. Again, this application, if I want to see the path, the best path from latency point of view, I can highlight it and it shows me that it's taking 2 LSPs to reach that from that PE to this particular applications. And I look in the right side, I can see a little bit more details. It tells me the total latency and how the latency is fragmented through from the PE all the way to the particular application. This happening in the background is happening on a regular basis. We measure the latency and we track it, and every time there's a better path, it gets updated automatically. Yeah. We do also offer, we've been working with some service operator where they want to inject their own latency to the applications. We have full REST as well as Kafka notification for integration with other external applications. So an operator could be injecting those latency values directly into the application on a regular basis, and the application will just react to those based on the best latency. Something to add?
Yeah, I just wanted to mention what I mentioned before about the path computation. To realize this use case, we need to have really a path computation on the whole thing, not just today. Most of IP networks, we focus internally, we improve, we optimize internally with our traffic engineering capabilities. But when it hits the border router, it's like going internet, you may not have the best here, but okay, you have the best here, the end-to-end may not be the best. So to add the value of the use case, the path computation has to really focus on just the end-to-end, including the latency within the MPLS tunnels. So they become, to the path computation algorithm, as just normal links, as a factor used into the path computation for what's the best border router and what's the best that will lead us to the best destination, including if that border router is multi-homed to multiple ISPs. So we compute as well within that segment.
I have some questions around ingress manipulation. So a lot of times, you've mentioned communities, you've mentioned some other, some other mechanisms like that. But oftentimes, there's many networks who just don't care, right? They're not going to respond to the things that you send them. Even ASPath doesn't really effectively change their routing policy. Oftentimes, a lot of ingress traffic engineering is by just shortest prefix, right? So do you have a mechanism, like if you have a broader range of prefixes, to use that lever as well, or is that?
That's actually a very good question because, and we see it as well. So when we talk to, let's say, service providers, they tell us, what if because you see, the inbound is exactly these two things, right? You can do things, but the decision will be your neighbor who's going to decide how traffic you're going to be receiving. So what we come up with, in fact, there are two categories of users of that inbound. There are those who, in order to make it deterministic, such that when he shifts traffic, he's sure he's going to get to the alternate. The folks are using what we call the blocking approach, which is accept community and block the community. So your prefixes now are tagged with that community. So if they accept it on one link, they know, and they block it anywhere else, they know that traffic will only come to that. The neighbor will only compute the path that will only get into your desired shift. For that, you don't have problem. There are a number that are doing that. The problem is if they are playing with AS prepend, for example. AS prepend, okay, I give you like this one is better, the other one is better, and so on. If they don't respect what the algorithm does, it's not like magic in that place. It's only what within the possibilities. So if he sees that he doesn't respond, we'll try, for example, if the policy allows, can you move to a blocking approach? Then we force the prefixes. So by forcing the prefixes by forcing the communities to be only on specific, and you control, the automation controls all the peering, you have a deterministic solution. If you do manual, you don't have it, because manual, you have to use the AS prepend, because that's the way we think as human, right? But if you are working with an algorithm, then you have a choice what the model you want to use.
So you're actually extracting or removing viable paths as options when you choose to use this other one as an ingress.
That's right. And where you're going to send them, you may choose not one, you may set multiple, according to redundancy policy that you put.
Gotcha.
So it's like a shift, right? Now you're working in full automation, then we have to think differently than the way when we operate the network, the way we're doing it today, right?
Right, because we have control of all of our periods.
Exactly.
That makes
exactly.
sense. Okay, thank you.
Thank you.